It's 10 o'clock and we might start the next seminar of Polish NMR Seminar Series, Volume 4. Today we'll have a talk by Dr. Habilitowana Marta Dudek from Center of Molecular and Macromolecular Studies, Polish Academy of Science in Łódź. And her title would be NMR Crystallography Organic Solids and at High Magnetic Fields when Resolution Matters. So Marta, the floor is yours.
Thank you. I'll just start sharing my screen now. Okay. Thank you for a nice introduction. I think this is a great opportunity for all our community to meet regularly in that way. So thank you for organizing this. Today I will be showing you some of our recent and not so recent results on NMR crystallography, but because of the nature of this meeting, I will also give some brief introduction into NMR crystallography in itself, as well as what we do in Łódź. So this is my very biased view. We are in Poland, and in the center of Poland there is Łódź. And in the center of Łódź, more or less, at least, there is my institute, which is called Center of Molecular and Macromolecular Studies, CMMS of Polish Academy of Sciences. And maybe not so much in the center, but in my personal view, it is in the center. There is a division of structural chemistry in our institute. And inside this division, there is my team, which is called Crystal Chemistry and Engineering Team. So we are part of Division of Structural Chemistry, and we are closely collaborating with Professor Marek Potrzebowski, who is the head of the whole division, and he also leads his own team of structural studies. So I grew up from this group of Professor Potrzebowski, and quite recently actually started to lead my own team. We are, as you can see, a very small team of 4 for now, but I will allow myself to start with this short announcement. We have a vacant PhD position. So if you hear about anything, or maybe you are interested in joining our team, please do contact me. This position will not be involving that much of NMR, but definitely there will be an NMR component to it. So we are actually doing some solid state NMR stuff, but my team is mostly focusing on understanding crystallization of organic molecules, understanding polymorphisms. So we are using NMR as a tool to help us understand this, in particular in structural studies. So in Łódź we have 4 Bruker NMR spectrometers. We have 2 spectrometers that are dedicated for liquid NMR measurements. This is our newest purchase, which is used by the whole institute. We have 500 megahertz, which is also dedicated to liquid NMR measurements. And we have 2 spectrometers, which we are using mostly for solids, although 600 megahertz has also capacity to measure, to do liquid NMR measurements. So I will be showing the results not only from these spectrometers, but also from our recent measurement session at 1 gigahertz and 850 megahertz at the University of Warwick. So first, because maybe not all in the audience, not all the people are very familiar with solid state NMR, a very brief introduction to it. So we know that in solution we have those random motions that averages out dipolar interactions, and as a result we see very narrow signals. But in the solid state, this is definitely not the case. And if we were to register solid state NMR spectrum carbon-13, solid state NMR spectrum of alanine, so very simple molecule, doing the pulse, using the pulse sequence we use in a solution, we would see something like this. So this is not something that we want. And the line widths in solids are very wide. So the spectra are not at all resolved, one may say. And this is all because of the two main culprits, dipolar couplings, interactions, and chemical shift anisotropy. So both of those phenomena are not averaged out as they are in solution, and we have to do something with them. We are lucky enough that both of them depends on the term which contains this cosine squared of theta. This theta angle is the angle between the external magnetic field and the nuclei of interest. So if we can get this term to be equal to 0, we can effectively average out dipolar couplings and chemical shifts anisotropy. So this is what we do in solid state, most of the solid state NMR measurements. We are putting our sample under the magic angle, which is 54.7. So if you calculate this term for this angle, you will see that this will be equal to 0. And if we are able to spin fast enough, so that faster than the strength of those interactions, then we can effectively average them out. The problem is that we are not always able to run this fast, because some of those interactions are in the range of 200 kilohertz or more, especially proton-proton dipolar couplings. Anyhow, by running such measurements using specifically designed pulse sequences, we can get closer to the spectra we have in solution. And actually now we can spin quite fast. This is not the most up-to-date picture. It shows different solid-state NMR rotors. So the containers in which we put a solid-state sample to measure it. So the smaller the diameter of a rotor, the faster we may spin. So we are mostly using in our applications 1.3 millimeter rotors, and in that kind of rotors you can usually spin with the spinning speed of 65-70 kilohertz. The smallest rotor for now is 0.4 millimeter. I don't know if this is already available commercially, but Bruker made such a rotor. It's really, really small. So to pack it, you actually need to do that under the microscope. And obviously the amount of sample you can put in there is very small. And in 0.4 millimeter rotor, you can spin 160 kilohertz, which is really, really fast spinning, although probably not all the interactions would be averaged out. So now let me say about a few words about NMR crystallography itself. So this is a technique we are using when we want to do solid-state NMR on crystals, and we want to establish their structure from the NMR spectra. So there are different approaches to NMR crystallography. People define it differently, but mostly we are combining solid-state NMR measurements with DFT calculations. And by doing so, trying to either build a structural model which can well describe our crystal, or refine this model, or maybe validate it. It can be differently. I will tell about it in a few seconds. And more often than not, we are also using powder X-ray diffraction crystallography, because NMR is very local technique, so it does not give us much information about long range order, and for that we need some diffraction-based technique. So why do we need at all NMR crystallography? I think this is quite obvious for many of us. In many cases, we are not able to crystallize crystals of sufficient quality to put into single crystal X-ray diffraction machine. So we cannot determine the structure from single crystal X-ray diffraction. This is definitely the method of choice, but it cannot be always used. It is also not that efficient in establishing hydrogen atom positions, for which examples I will be showing in a second. We might argue that there are some different techniques. We can solve the structure from powder, that's true, but we also have problems then with hydrogen atoms. We have micro electron diffraction. This is an excellent technique, but it also is very, it's capricious, so that it's not always easy to get a crystal. So micro ED electron diffraction has actually problems opposite to single crystal X-ray diffractions. So many crystals are too large for it. We have also severe radiation damage. So this is also not a universal technique that we can use for all the solids. So NMR actually does not have these limitations. Solid-state NMR can be used for whatever crystal we have, even for amorphous solids, and people are deriving many structural informations about amorphous samples from solid-state NMR spectra. Although it has different limitations, and not the least of it is that we have more often than not the severe signal overlap. We have problems with assigning all the signals, as well as it is not so straightforward to build a structural model basing on the NMR spectra alone. So when you think about NMR crystallography, there are actually three main possible scenarios, and people use them in those three ways. So you can have a reasonable structural model from either powder X-ray diffraction, indexing, and Rietveld refinement, or from micro ED. And you use solid-state NMR for validation purposes. So you have like a ready structural model when you start doing NMR experiments. And then for this model, you can calculate NMR parameters in DFT codes. So that's allow you to run calculations under periodic boundary conditions. So for a unit cell of a crystal, and then you can compare those calculated theoretical values of the shieldings, chemical shieldings, with your experimental chemical shift values. And here, proton mass experiments are the most informative, because protons are the most sensitive to any local changes in the crystals. And if you have the agreement, which is good enough, then in that way you can validate the model. What does it mean, good enough? That's always a valid question. It's hard to definitely answer this, but we usually assume we calculate root mean squared deviation for all the pairs of predicted and experimental chemical shifts. And we assume that if we have RMSD value for protons below 0.5 ppm, and for carbon-13 below 2.5 ppm, then the agreement that you have is thought to be sufficient. Those values are, of course, from benchmarks. So if you take a crystal which is determined depending on the nature of this crystal, nature of a compound, determined by single crystal X-ray diffraction, calculate the NMR parameters and compare them with experiments, you will get an agreement below those values, definitely. So this is how it works. It can also be used if we have several models from indexing and Rietveld refinement. It can sometimes happen, and this actually works. This approach, this is one of the first examples by Lyndon Emsley, published in 2010, of thymol, which is for which they had several different models, and you can see that only one of them, this third model, gives the RMS error value below 0.5 ppm. So the second approach, the second scenario, involves difficulties in building a model from powder X-ray data alone. This can often happen. So we can use solid-state NMR as a source of structural constraints. So this is a recent example from our team. So our work in collaboration with Professor Potrzebowski's group of the structural determination of this co-crystal of a antibiotic linezolid with this conformer here. I will say a few details about the conformers. So, so to do that, you really need to put a special attention to all the details in the NMR spectra. So in this case, we were able to determine the conformation of linezolid inside this crystal because of the interactions that we saw in the 2D spectra. We saw that this C6 carbon is in close proximity to this H12 proton. We also were able to determine the conformation of this molecule because of the hydrogen atoms that can be pointing in different directions. It can be really challenging. And then this model was used in further studies and refined against the experiment. And finally, it is also very much possible and often encountered that neither NMR no powder X-ray diffraction data can give you an appropriate model to calculate and to evaluate. So in these circumstances, we often use crystal structure prediction calculations, which generate hundreds of thousands of crystal structures. So what you see here is actually the result of such calculations. So the plot of the total energy of crystals against density, and each dot on this plot represents a different crystal structure. So we can generate and then energy minimize many of such crystal structures. This is, of course, computationally expensive, but we can use experimental data to narrow down the search space that we need to cover. And then we take the lowest energy region of this landscape, so all the structures that falls, let's say, within the first 20 kilojoules per mole in their energy above the minimum structure, and calculate NMR parameters for those structures. So as is shown for this molecule here, epicatechin. Here again is a similar plot as the one we saw for thymol. So we plot RMSD, proton RMSD values against the structure rank, which is derived from their relative DFT energies. And we are searching for every structure that falls beneath a cutoff line, which is, as I mentioned, typically 0.5 ppm for protons, a bit more for carbons, and 5-6 ppm for nitrogen if we have a nitrogen atoms in our molecule as well. So as you can see here is only this one structure, and this is also a structure with the lowest energy. And if we find something like this, we can safely say that we found a model, a crystal structure which sufficiently well represents a real crystal structure that we have in our laboratory. So in that way, we can have the results in a similar manner from using solid state NMR data in a similar manner as we have from a single crystal X-ray diffraction crystallography. So if you're interested in reading or learning a bit more about using CSP and NMR crystallography, there is this recently published book, which was edited by David Bryce, and which is covering all the areas of NMR crystallography, but in particular, it also says about calculations of NMR chemical shifts and about the usage of CSP calculations with solid state NMR. So the thing that I will be mostly focused on today are binary forms of meloxicam. Meloxicam is anti-inflammatory drugs. And what I mean by saying binary forms is the crystals in which, in a crystal lattice, at least, or actually for binaries, there are exactly two molecules are bound together in one crystal lattice, and they can be either co-crystals, so then the neutral molecules are bound, so through the intermolecular, when I say bound, I mean intermolecular interactions, so weak interactions. They are together in a crystal lattice, in a unit, in a crystallographic unit cell, or when there is a proton transfer, we say about the formation of salts. And those two entities are different, and Food and Drug Administration differentiates them. So it is also very important because of the regulatory reasons that we have tools that allow us to differentiate between those two cases. So in our studies, we were actually interested not so much in obtaining those forms, but in discovering new crystallization pathways for elusive polymorphs of this molecule. And we thought that we can do this through the co-crystallization with those molecules and then removing them from crystal lattice. So this was the approach that we tested, but in the meantime, we obtained a lot of different forms of meloxicam with those coformers, pyrazine, pyrazole, and imidazole. To move forward, we needed to determine their crystal structures. So for pyrazole, we got two different polymorphs. They are both 1-to-1. And as you can see, we were able to determine their structures through single crystal X-ray diffraction. So as it will turn out, this is not the whole story about those polymorphs. Then for a second coformer, we obtained actually 6 different crystal forms, binary forms or tertiary forms, so containing another component. In this case, this was a solvent molecule in different ratios. So this was actually a very complicated landscape. And finally, one co-crystal for meloxicam and pyrazine. So for this variety of forms, actually only for 3 of them, we got single crystal X-ray diffraction results, despite many, many efforts to get some more. Let me start with showing you some of the solid-state NMR spectra for meloxicam pyrazole polymorphs. So as I mentioned, we determined those structures from single crystal X-ray diffraction, and actually both solutions were excellent. So there was nothing that caused our concern. Those structures were evaluated by crystallography specialists, and they say, well, they are definitely very well resolved structures. We see nothing of concern in thermal ellipsoids, but we were, one might say, too thorough with our experimental approach and decided to register solid-state NMR spectra. At first, we planned only to register simple CPMAS experiments, so one-dimensional experiments for carbon and nitrogen atoms. And indeed, for carbon-13 NMR, we saw what we kind of expected, because those crystal structures are quite similar. So we expected similar chemical shifts of carbon-13, which reflects similar environment in a crystal. But when we run nitrogen-15 CPMAS experiments, we saw something which could not be explained by the crystal structures that were determined through diffraction methods. This gets us wondering what's going on in the system. So then we calculated NMR parameters, NMR spectra for the structures that we got from the single crystal X-ray diffraction. And you can see that for form 2, the agreement between this calculated red spectrum and the experimental purple one is really good. Nothing to worry about. So we were able in that way to say, okay, this structure is verified by our solid-state NMR measurements. This is that kind of interaction, as you see here on the slide, is actually what we see in real life. But this was not the case for form 1. So we need to resolve this puzzle, and actually the only signal that matches here is this methylated nitrogen from meloxicam, and all the rest of the nitrogen atoms chemical shifts are very much off. So we immediately assumed that this is because of the protonation state of those molecules, that something has to happen here. So if you think what are the possible solutions to this, you can quickly come up with four, let's say, border possibilities. So you can have either a tautomer, which was determined from single crystal X-ray diffraction. This will be called as tautomer 1. But you can also have a reverse situation. Then this molecule can exist in this different tautomeric form, and it will have definitely different chemical shifts. But you also may say, okay, but why exclude proton transfer? That's true, we could not exclude it from the very beginning. So we also can have salts in which both protons, although they are not very much probable because of the pKa values, but still we evaluated this possibility. And both protons can be either on pyrazole molecule, on meloxicam molecule. So then we run proton MAS experiments under very fast magic angle spinning at low temperature, or actually in the whole temperature range up to 173 K. And we did not see any signal moving. So this could happen if we were to have this proton transfer. So at lower temperatures, we should see some additional signals appearing. We also didn't find those two salt structures stable in our DFT calculations, so they converge either to one or the second of the tautomers. So we excluded them further. But when we calculated those two tautomers and calculated nitrogen chemical shifts, you can see that those RMSD values for neither of them is in agreement with experiment. They are really, really off. We should see here something below 6 ppm, 6 or 5 even ppm. But what we noticed is that the points, different points for different nitrogen atoms lie on the opposite sides of the trend lines for the two opposite tautomers. So we thought, okay, this seems like averaging of the structures. So maybe we have something in between. So a very fast exchange between those two tautomers, so fast in the NMR time scale that we see actually averaged chemical shifts. So we then decided to calculate weighted averages of the chemical shifts using different percentage of tautomer 1 and tautomer 2 and calculated RMSD values for that kind of averaged structures. And what you see here is a plot of the dependence of this percentage of X-ray H position motif against nitrogen 15 RMSD. And we have a very nice minimum here, which is definitely below 6 ppm cutoff line. And this structure corresponds to 70% of one tautomer and 30% of the second tautomer. So this is one of a very rare examples of NMR determined occupancy. So we can now show to all the crystallographers that, look, we can do with NMR what you can do with single crystal X-ray diffraction measurements. We can actually determine the occupancy of two different sites in a crystal. And this phenomenon is not visible because of a low electron density on hydrogen atoms, especially between those two electronegative atoms. We do not see them through single crystal X-ray diffraction. So finally, this will be the experiments performed at the University of Warwick. We registered to have a final confirmation. We registered two-dimensional proton detected nitrogen 15 and nitrogen 14 NMR experiment. And as expected for Form 2, there was nothing suspicious, again confirming the diffraction-derived crystal structure. And for Form 1, we indeed saw 4 correlation signals corresponding to 4 different sites in this crystal. Again, confirming this 0.7 to 0.3 ratio. Now, before I show you some experiments very briefly from nitrogen 14 measurements, let me say a few words of introduction, because maybe not all of us are familiar with the difficulties we encounter when measure nitrogen 14 NMR, solid state NMR spectra. So this is, we all know, a quadrupolar nucleus. It has moderate CQ values, which is not that bad, but still causes a lot of troubles. So in these circumstances, the experimentally observed shift is not actually a pure isotropic chemical shift, even under the magic angle spinning, but is a sum of isotropic chemical shifts and the so-called QIS, which is isotropic quadrupolar shift, which arises from quadrupolar interactions. And the issue is that this QIS depends on the resonating frequency. This is nitrogen 14 resonating frequency. So it will hugely depend on the magnetic field strength. So on the magnet on which we are measuring our sample. And we cannot say a priori what is this QIS value and what is the isotropic chemical shift. So we have difficulties in comparing the calculated NMR parameters, so chemical shifts, with those determined experimentally, because we don't know those two values. We know what is their sum. So in this equation for QIS, we have here this resonating nitrogen 14 resonating frequency, but we also have here a PQ value, which is a quadrupolar product, which contains information about quadrupolar coupling constants, as well as asymmetry parameter of this quadrupolar tensor. So if we think about determining this PQ values, which are very sensitive to the local environment, to the dynamics, to proton positions in particular, we need to say what is the contribution of those two values. So to do that, we can register nitrogen 14 solid state NMR experiments under various magnetic fields. So here is on the x-axis, there is 1 over Ni 0 squared plotted, which corresponds to the magnetic fields, the magnetic field values. And here we have this observable nitrogen-14 shifts. And we expect the values of this nitrogen-14 shift to have linear dependency on 1 over μ0 squared. And the B value from this equation should correspond to this isotropic chemical shift of nitrogen-14. And the A value is depends on the quadrupolar product value. And from this, we can easily determine PQ value. So you see that in order to determine this PQ value experimentally, we need to have measurements on at least 2 magnetic fields. It is actually more common to register it at moderate magnetic field strength, so not as we did at 1 gigahertz and 850 gigahertz, but as you will see, this can also give you a sufficient number of information. So this is an example of histidine. PQ values for histidine, you can see that they are different for each of the nitrogen sites, and this depends on their mobility, their proton substitution, and the NH distance as well. This is the experimental result we got for form 2 of meloxicam, despite many efforts on neither of the magnetic field strands, and we tried on, if I remember correctly, on 4 different magnetic field strands. So 1 gigahertz and 850, 700, and 600 megahertz. In neither of them, we were able to got any THMQC signal. We assume this is because of the dynamic exchange in form 1, but in the form 2, in form 2 of this co-crystal, you can see this. So this is a THMQC proton detected nitrogen-14 experiment. So the black dots are from 1 gigahertz, and you can see 2 NH sites as there should be. And for 850 megahertz, there is only 1 site visible. And this is because when you plot those values on the dependence, as I showed you before, on the 1 over μ0 squared, you will see that that at this magnetic field strength, those values are should actually be the same. So what we can see here are the equations that we got from those experimental points. And what is important here is that those B values that we got from this equation are in very close agreement with the nitrogen-15 isotropic chemical shift, because we assume that nitrogen-14 and nitrogen-15 isotropic chemical shifts should be the same, at least in a more or less, so to say. So you can see that both values for both NH sites are in agreement with what we saw from this plotting, and we were able to determine PQ values. They were also in very good agreement with the calculated ones. So now briefly about the second second system, we studied meloxicam with pyrazine. So in this case, we did not have any crystal structure from single crystal X-ray diffraction. When we registered solid state NMR parameters, we saw that the order of the chemical shift resonances should correspond to a Zwitter ionic form of meloxicam. So this comes from our earlier studies. So meloxicam can actually easily exist in its enol form in crystal structures, but there can be a proton reordering in this structure, and it can exist in Zwitter ionic form. So in many structures, it exists in this form, for example, in DMSO solvate, and you can see that, or similarly in a hydrate, and you can see that then the outlook of the signals that are marked with colors here is different. And this was what we saw in meloxicam pyrazine. So we immediately expected this Zwitter ionic form to be present. We also saw from nitrogen 15 experiments that there is only one NH signal from pyrazine. So we assumed that there is a half of pyrazine molecule in the crystal. Fortunately, we were lucky enough to get a crystal structure from powder X-ray diffraction. So this is a solution from powder X-ray diffraction, but there are no hydrogen atoms. But what we saw there is that this is not what we were expected. This is an enol form. This is not this Zwitter ionic form, which we assumed is present in the crystal from carbon-13 CPMAS measurements. So this came quite as a puzzle, and we needed to put hydrogen atoms somewhere in this molecule. So what we did then, we first register double quantum, single quantum, proton-proton correlation at 1 gigahertz. And this gave us a resolution sufficient enough to assign the particular sites, especially for aromatic carbon atoms. And what we saw is that this NH nitrogen correlates indeed with the signal from pyrazine. So this NH nitrogen can be then either here or here, and this correlation should be observable. But we also saw a correlation of this NH nitrogen with a thiazole proton. So this is this proton which should be here, and as a result, we thought that the best explanation is when a hydrogen atom will be actually on this thiazole, in this thiazole ring. So placed here, and the tautomeric form, which is present in this meloxicam co-crystal, is apparently a form which was never before encountered in any of meloxicam crystal forms, in which there is this stabilization as present as in enol form, but nitrogen atom is located on the thiazole ring. And final confirmation came from determining the PQ values for as I showed you in a similar way as I showed you for meloxicam pyrazole form 2 system. And finally, when we did the calculations and compared experimental and calculated PQ values, they are in excellent agreement. And the same goes for RMSD values for nitrogen and proton experiments. So this is the structure with final refinement R factor of 3.2%, which is excellent for that kind of solution. So last systems, very briefly, are meloxicam imidazole systems. So we start with the comparison. I will be talking only about those two systems mostly. So we start with comparison of nitrogen 15 CPMAS spectra, and you immediately see very different chemical shifts of those nitrogen 15 resonances. So this is, for the sake of comparison, a nitrogen 15 spectrum of a salt, salt solvate of meloxicam imidazole, which was determined through single crystal X-ray diffraction. So from this, we assumed by comparison that this should originate from a salt and this one from a co-crystal. But note that here are very broad additional yet unexplained signals. So first, we are looking at the high field NMR measurements for one-to-one system. This is nitrogen 15 head core experiment. And this is these are two overlaid spectra from 1 gigahertz and 850 megahertz of THMQC proton detected nitrogen 14 spectra. And what we see here are 3 NH sites with different PQ values. And this can happen if we have situation like this. So there are two, as expected, two protonated nitrogens in imidazole molecule, and we have a NH proton. So there is no OH signal here, but NH proton on this meloxicam nitrogen. So because we did not have a crystal solution for this crystal, we decided to do CSP calculations. So this is a CSP plot of the relative energy of the lowest energy structures we got from CSP calculations against density. And you see that there is this one nice minimum energy structure. And when we calculated the RMSDs, nitrogen 15 RMSDs for all of those structures, you can see that there are few of the structures that fall below the 5 in this case, ppm cutoff line. Among them, there is this first structure, but there are also 3 other structures. Fortunately, they are very, very similar to this structure. This is one thing. And the other thing is that this structure here has very low energy, so actually the lowest energy. So it corresponds to the real model in the best possible manner. So this is this structure here. And indeed, calculating it and comparing experimental and calculated PQ values confirmed this protonation state of meloxicam and imidazole in this crystal form. And finally, the last crystal form was also solved from powder X-ray diffraction without the protonation state. And we determined this protonation state using solid state NMR experiments. Again, nitrogen 15 and nitrogen 14 measurements, from which we were able to determine that one of the imidazole molecules is indeed in its neutral form, but there is a proton transfer from meloxicam to the other imidazole molecule. So it's actually not a co-crystal, but well, one may say a salt co-crystal, in which only one imidazole molecule is protonated and the other is neutral. And finally, the comparison of the experimental and calculated PQ values as well as RMSD values in excellent agreement with what we saw. And what is also interesting is that we, in the nitrogen 14 spectra, we also could not see any signals originating from this doubly protonated imidazole. So this cation. We assume, so if you recall, they're on nitrogen 14, we can see here on this projection here that those nitrogens are very, very broad, and the same can be said about their protons. So this proton actually correlates not with this signal, it might not be that well visible, but with this very broad one. And this proton correlates with this very broad signal here. And this larger nitrogen 15 correlates with the NH signal here. So this again is a case in which we could not determine the PQ values or register any signal for that matter for this very broad resonances, probably because of the broadening of the resonances. So that's more or less everything I wanted to share with you today. So we are quite happy that we are now able to derive NMR occupancies from solid-state NMR spectra. And if you're interested in molecular crystals at all, I encourage you to try to determine those PQ values for the nitrogen through the nitrogen 14 experiments. They are really very informative and very useful to unambiguously determine the type of the NH site we are dealing with. So with this, I would like to thank my group, which was involved in this, but also Marcin Oszajca, who is from Jagiellonian University, and Piotr Paluch, who was with me at the University of Warwick. Here is a picture of this 1 gigahertz magnet, so you can actually easily sit underneath, and Panacea, which allowed us to conduct those measurements, who actually paid for not only for the measurements, but also for our stay here. So I'm really grateful for this funding. And thank you for your very kind attention.
Thank you, Marta, for a great talk. And we are open for discussion. If you want to ask questions, please turn on your microphone and camera. If you cannot, if your microphone doesn't work, write on chat the question. So we start. Okay, so maybe ask a short question. So you mentioned with the PQ measurement that usually people recorded on lower fields that you did. Is it because of the scarcity of ultra high field machines, or there is some physics behind it?
Yes, there is definitely physics behind it. It hugely depends on the PQ values, but you can, for example, see here that at higher magnetic fields, those signals are closer together. And because of this reverse dependency on the resonating frequency of the PQ value, usually you get the best signal separation at moderate magnetic fields. It's not a rule because it hugely depends on the PQ, but this is something which we often see. So the lower the magnetic field, the larger the signal separation you will have.
Okay, thanks.
I cannot find how to ask for the voice, but if nobody wants to...
We hear you, so it's fine. I think Vivian Agarwal is also in the light.
So after is related to electric field gradient in the position of nitrogen 14 nuclei. So this is just, so if you have very symmetrically surrounded nitrogen, then PQ is small, and so on.
Yeah.
So this is the physical explanation.
Yes. Yeah. I agree. Yes.
Okay.
I think Vipin also wants to ask the question, but I don't think your microphone is working.
Oh,
Now we hear you. Yes.
Okay. Hi, Marta. Thanks for a very nice talk, and thank you for the organizers for this series. In the second example that you gave, you had you talked about disorder on the imidazole ring, on the doubly protonated imidazole ring. Is this a static disorder or a dynamic disorder in the crystal?
Well, I cannot answer it definitely. I would go with dynamic disorder, but it's so because we do not have single crystal X-ray diffraction results to establish what's the case in here. We only have, well, let's say, indirect results from NMR measurements. But I would say this is a dynamic disorder, which is often the case with imidazole. So it would not be that surprising.
Okay, because since you have these extra protons, could it be that the hydrogen bonding is not really symmetric and you actually have protons that are sort of distributed all over the place? That would give rise to a static disorder also.
Yes, it is possible. Yes, definitely.
Okay, thank you.
Thanks.
Potrzebowski.
So, Marta, congratulations, nice talk. So my question is related with this co-crystal meloxicam when you have an H bridge. So did you consider to use deep shift techniques for precise localization of a proton in such a bridge?
You mean like CPVC experiments?
No. So maybe like a Paisima or something like this.
Right.
For
Okay.
study of dipolar interaction in order to see what is distance between a nitrogen and what is a localization of this proton in this NN bridge. So probably technically it is a very demanding experiment at natural abundance. But you have several options, DNP or something like this.
Yeah. You know that my experience with DNP is not that great, but maybe one day. I mean, in terms of, I tried run DNP experiments on actually 2 or 3 systems, and in neither of them it actually worked or provided any reliable information. But maybe that this is just my bad luck. But in this case, you see that the spectral resolution for protons is well, very bad, I would say, for this form 1 of meloxicam pyrazole co-crystal. So we do not see we see both or actually all 4 NH resonances at one side. So I'm not sure that we will be able to see this experimentally, but maybe through PSEMA it's could be possible. Yeah, I mean, we didn't try. We also do not see any averaging of the distances from the crystal structures, C and distances. So that is why we thought that this is actually a fast exchange between the 2 states and not that the protons are somewhere in between, although we cannot exclude this.
Any other questions? I don't see, so let's then switch to the advertisement of our next seminar. So in 2 weeks, we meet in the news way of seminar. So instead of scientific seminar, we'll have more like a topic that is in the interest of many people in our society. So the pitfalls of acquisition of NMR spectrometers, which will be given by Dr. habilitowany Piotr Bernatowicz from Institute of Physical Chemistry, Polish Academy of Sciences, who is right now in the middle of installation of our two consoles from Bruker, and he will give a talk about what to expect when you already get the money and want to buy a spectrometer. What can happen there? And I encourage all people who were in a very similar situation recently to join us and share during the discussion their story too. So see you in 2 weeks. Thank you very much for joining us this time.
Thank you.